Today we're continuing with proof techniques for demonstrating the correctness of greedy algorithms, and we'll be specifically focusing on exchange argument proofs. We'll demonstrate this by proving the correctness of a greedy algorithm for another scheduling problem. This time, the scheduling problem that we'll focus on is about minimizing the maximum lateness of a set of requests with deadlines. So in this problem, we have a collection of requests, but now they are each characterized by a deadline by which they are supposed to be accomplished and an amount of time required to complete each task. Unlike our last scheduling problem, our goal is now to schedule all of the requests by choosing a start time for each such that no two tasks overlap, and our overall goal is to minimize lateness. We will score any given scheduling of the requests by the maximum lateness of any individual task. And the lateness is the time at which we finish the task, which is the start time plus the length of the task, minus the deadline, or 0 if we finish before the deadline. So over all of the requests that we schedule, we will figure out the lateness of each individual request, and we will score our schedule based on the worst lateness of any individual request. And an optimal solution to this problem will find a schedule that minimizes this worst-case lateness. Our greedy algorithm for this problem will, as usual, be quite simple. We'll sort all of the requests and then line them up back to back. So our greedy algorithm is to simply schedule all of the tasks back to back. The first request will start at time 0, and each subsequent request will start at the finish time of the previous one. But again, I have left unspecified the criterion by which we will sort all of the requests to build this back-to-back schedule. So let's consider a few possible criteria in the context of an example problem. Here we're given 4 requests that each have a deadline and a time required to complete. And some obvious criteria to consider for sorting these tasks are the deadlines, or the lengths, or the difference between those, which we'll call the slack time. If we think of our example problem as perhaps scheduling the things that you need to do for homework, we could imagine plausible justification for any of these criteria. The length criterion is saying, get the shortest assignments out of the way first, and then move on to the ones that will take longer. The deadline criterion is saying, prioritize the things that are due soonest. And the third criterion is considering when is the task due and how long before that deadline do we have to start in order to get it done, and then sorting by that slack time for each of the requests. So let's think about what would happen if we ran our greedy algorithm on our example set of requests using each of these possible criteria. If we sort by the length of the task, then the shortest is request 4, then 1, then 3, then 2, and so that gives us our schedule. And to evaluate how well we've done, we should consider at what time do we complete each of these requests, and how does that compare to the deadline to get our maximum lateness over all of the requests. We schedule the first request to begin at time 0, and so it will be done at time equals 2. Then the next request gets scheduled as soon as the first one completes. So request 1 will begin at time 2 and complete at time 5. Then we'll immediately begin request 3, and it will last until 9. And finally, we'll start task 2, and it goes from 9 to 17. And if we compare each of these finish times to the corresponding deadline for the request, then the requests have latenesses of 0, 1, 2, and 7, which means that our worst case lateness overall for the schedule is 7 from request 2. If we instead sorted by deadline, then we would put request 1 first, followed by 4, then 3, then 2. Then, if we schedule back-to-back in this order, starting at time 0, we will finish request 1 at time 3, then request 4 at time 5, then at 9 and 17. And in this case, we finish the first 2 tasks before their deadline, but we're still late by 2 for request 3 and late by 7 for request 2. Giving us, once again, a lateness of 7 for the schedule overall. To sort by slack time, we need to calculate the difference between the deadline and the length of each request. And so we end up scheduling the requests in order 1, 2, 3, 4. And if we calculate when each request finishes, we get 1, 11, 15, 17. And that gives us a lateness of 0 for the first request, 1 for request 2, 8 for request 3, and 11 for request 4. And so right away we can rule out the slack time criterion. We have a counterexample showing that it doesn't give us an optimal algorithm. But between the other 2 criteria, we have the same lateness for our schedule. So I will leave it as an exercise for you to devise an example that shows that the length criterion can sometimes give us a suboptimal schedule. And in the rest of this video, we will prove that the greedy algorithm with the deadline criterion gives us an optimal algorithm for the minimizing maximum lateness problem. To prove the optimality of our greedy algorithm, we will use an exchange argument. The idea of an exchange argument is that we will hypothesize some optimal schedule, and then we're going to make swaps that can only improve the lateness of the schedule to transform that hypothetical optimal schedule into the schedule produced by the greedy algorithm. And if all of those swaps done during the transformation don't make the schedule worse, then our schedule must be as good as any other. In this case, our exchange argument relies on this set of facts, each of which we will need to prove, and several of those facts are about the idea of an inversion in the schedule. If we think about some schedule where we begin at time 0, and then we schedule some task to run to completion, and then after that we schedule some other request, and so on. An inversion is a case where we have one request, Ri, that occurs earlier in the schedule than some other request, Rj, but where the deadline for Rj is earlier than the deadline for Ri. And since our greedy schedule is one where we ordered everything by the deadline, our greedy schedule has no inversions. And so the exchanges that we're going to make are primarily about removing the inversions from some other schedule and showing that every time we remove an inversion, that only makes the schedule better. And eventually we can get to the greedy schedule having improved from whatever schedule we started with. In a moment, we will prove all 5 of these facts one at a time. And when we do, we will then have the basis for our exchange argument. But to know where we're going, I think it helps to lay it out first as though we had proven these facts and think about why this proves the greedy schedule to be optimal. So our exchange argument will be taking any arbitrary schedule and transforming it to be more like the greedy schedule. First, if there are any gaps where one request finishes and then we're not working on anything before starting the next request, we will squish out all of those gaps so that all of the tasks are undertaken back to back. If we are right about fact 1, this will only improve the overall lateness of the schedule. Then we will look for 2 tasks that are back-to-back in the schedule that are inverted, meaning the one that is scheduled earlier has a later deadline, and we will swap them. If we do that until no more swaps are possible, then we will end up with a schedule that has no inversions. The reason for this is based on facts 2 and 4. If there are any inversions in the schedule, even if they are between tasks that are far away, then by fact 2, there must be some pair of requests that are back-to-back in the schedule and inverted. And by fact 4, when we swap 2 back-to-back tasks that are inverted, that decreases the number of inversions in the schedule. And so we will always be able to find a back-to-back inversion, and we will decrease the number of inversions every time we do a swap. And so eventually we will have swapped away all of the inversions until there are none left. And if we do that, then by fact 3, every time we swap back-to-back inversions, we are only improving the overall lateness. And so this entire process of making swaps that remove inversions can only have improved the lateness of the schedule. At this point, we would have a schedule that is ordered by deadline, and no matter what schedule we started with, this new one is at least as good. But it might still differ from our greedy schedule in that there could be some tasks where our sorting by deadline didn't tell us what order to put them because they had the same deadline. And so fact 5 says that we can swap 2 tasks with the same deadline if they were back-to-back, and that doesn't change the lateness. And so we can take that schedule that has no gaps and no inversions and swap same deadline tasks to turn it into exactly the schedule that would be given by the greedy algorithm. And this whole process of making these exchanges to transform the schedule can only have improved the lateness. And so no matter which schedule we started with, even if it was the best possible schedule, all of these exchanges can only have improved it. They never make the lateness worse. And so the greedy algorithm must give us a schedule at least as good as any other schedule. And so it gives us an optimal solution to the problem. So if you believe all of these facts, we now have an argument for the correctness of the greedy algorithm. So what remains is to prove each of these 5 facts. For fact 1, when we compress the schedule by removing gaps, we are making the start time, and therefore the finish time, of any tasks that we move smaller. And so if we make the finish time smaller, that can only make the lateness of the task lower, and so we can only ever improve the overall lateness. It's possible that this won't change the lateness of a particular task, because it might already have a lateness of 0, and it's possible that this won't change the lateness of the overall schedule if we end up not moving the task that had the worst case lateness, but this will never make the schedule worse. For fact 2, our goal is to show that if the schedule has any inversion, then it has two tasks that are scheduled back-to-back that are inverted. And we will prove this by contradiction. So we're going to suppose that we have some inversion, but that the schedule has no back-to-back inversions. Since requests I and j are inverted, and I has the later deadline, that means that I is earlier in the schedule than j, and they can't be back-to-back since we're assuming there are no back-to-back inversions, so there must be some other requests scheduled in between I and j. But by the second part of our assumption that there are no back-to-back inversions, then that means that Ri and Ri plus 1 can't be inverted. And likewise, the deadline for I plus 1 has to be no later than the deadline for I plus 2, otherwise that would be a back-to-back inversion. And this reasoning proceeds through all of the back-to-back tasks because we have a gapless schedule, and will eventually arrive at the request right before j in this schedule. And its deadline has to be greater than or equal to the request that came before it, otherwise there would be a back-to-back inversion. And then the deadline for j has to be greater than or equal to j minus 1, otherwise we'd have a back-to-back inversion. But this contradicts the fact that we had an inversion in the first place. So our assumption must have been false. There must be a back-to-back inversion whenever there is any inversion. Another way to think about this is that if we at some point have to go down in terms of deadline to get from I to j, we can't have been going up the entire way. There has to be some point at which we drop down in order to get to the smaller deadline. For fact 3, we are trying to show that when we make our swap of back-to-back inversions, that's not going to make the lateness of the overall schedule worse. So let's think about two requests that are back-to-back and inverted. And we're going to be swapping these two inverted requests, so we'll end up with a schedule where j comes first, followed by I. And the first thing to note is that the start of these two requests is still at the same time, and the finish of these two requests is still at the same time. And so let's call that common finish time f. So before we swapped these in the original schedule, we know that they were inverted, which means that the later task had the earlier deadline. So if we add to this chart the deadlines for I and j, then we know that the overall lateness for this pair of tasks in the original schedule was based on request j. It's possible that these deadlines were somewhere over here, where the maximum lateness between I and j was 0. And if that's the case, then swapping them is definitely not going to change the overall lateness. So let's suppose for a moment that there is actual lateness, right? The deadlines are over here. Then, since J finishes later and has an earlier deadline, it's definitely the case that the larger lateness between these two tasks is from task J. And so our initial lateness comes from the difference between F and the deadline of J. But then, when we swap I and J, we now have J ending at this earlier time, which we can call F prime. And we know that F prime is less than F because we put request I in between. And so now the lateness of task J is only from its deadline up to F prime. But in our swap, we moved I to be later, and so it could be the case now that our overall lateness is based on task I. So the new lateness of I is F minus the deadline for I. But from the fact that these were initially inverted, we know that the deadline for J was earlier than the deadline for I. So after the swap, we don't know whether our worst case lateness will be based on I or based on J. It can depend how far apart those deadlines were. But either way, whether the new maximum lateness is based on J or based on I, it's definitely no larger than the initial lateness. And so by performing this swap, we have definitely not made the overall lateness of the schedule worse because we didn't change anything before this start point or anything after this finish. So if I and J were not the overall worst case before, they still are not. And if they were the overall worst case, we may have actually improved the schedule. Fact 4, that swapping two requests that are back-to-back and inverted reduces the overall number of inversions, should be fairly obvious. If those two requests were inverted and we swap them, now they are no longer inverted, and so we have decreased the number of inversions in the schedule by 1. But the reason this is worth stating as one of our facts is that when we made exchanges from an arbitrary schedule to the greedy one, we were removing one back-to-back inversion at a time, and so we need to know that this process will eventually get us to a schedule that has no inversions like the greedy one. So if every time we swap a back-to-back inversion that eliminates one inversion, then in a finite schedule, if we do this enough times, we must eventually get a schedule that has no inversions. The point of fact 5 is to argue that once we have gotten rid of all of the inversions, we can shuffle things with the same deadline around to exactly match the greedy schedule. And we can show this by considering two back-to-back requests that have the same deadline. If we have a pair of back-to-back requests with the same deadline, which could happen once we've eliminated all of the inversions from the schedule, then the lateness of this pair of events is necessarily based on which of the two is scheduled later. Because they have the same deadline, the difference between the finish time for I and the deadline has to be smaller than the difference between the finish time for I plus 1 and the deadline. And if we were to swap these, then the start time for the pair and the finish time for the pair would be unchanged, And so that maximum lateness for the pair also doesn't change. So if there is a set of requests that all have the same deadline, that are all scheduled back to back, then only the finish time of the last of those requests matters for the worst case lateness overall of the schedule. So now that we've proven all 5 of these facts, we know that we can take any schedule and transform it into the greedy schedule by swapping back-to-back inversions until there are none left. And that process can never make the overall lateness worse. And so, because we can transform any schedule, including an optimal one, into the greedy schedule without making it worse, we know that greedy is optimal, and so we have a correct algorithm for minimizing the maximum lateness.